Hi student, in this video, we will define the concept of eigenvalues and eigenvectors. These will form the most important facet of the structure of the theory of square matrices. Now, let's consider M star M matrix A. What is the eigenvalue of A? An eigenvalue of matrix A is a scalar such that the equation A V equals to lambda V has a non-trivial solution. That means that the vector V should be a non-zero vector. And this vector is called eigenvector. Now, what's an eigenvector? An eigenvector is a non-zero vector such that A V equals to lambda V for a scalar lambda. So there are two things that you must keep in mind here, that the eigenvector must be non-zero for a specific value of lambda, and number two, it must satisfy this equation AV equals to lambda V. Now, let's have a deeper look on the meaning of this equation. What does that mean to have an equation AV equals to lambda V to have a non-trivial solution? Now, V will represent a special vector for some special value, for some special eigenvalue lambda. What are we trying to say? We're trying to say that to solve this equation here, we need to find special vector V such that when V is multiplied by matrix A, the vector V will keep the same direction. Okay, so for example, Ax equals to lambda x, right? X being the eigenvector. So we are looking for special vector x such a way that being multiplied by the matrix, it still keep the vector x in the same direction. Now, we know that normally when we multiply a vector by a matrix, the matrix behaves as a linear transformation. So the matrix will either change the direction or orient the vector in another direction. But the peculiarity about the eigenvector is that being multiplied by matrix A, it keeps and preserves its direction the same. Now, let's have a look on some example to probe or to test to see if some eigenvectors are solution of this equation. Now, if we consider matrix A, let's say this is the first example. We say matrix A equals to 3, 1, minus 1, 3. Okay, minus 1 here. Okay, let's consider that this is a matrix A. This is 3, minus 1, 3. And let's check if this vector 1, 0 is an eigenvector of matrix A. How you do that? You have to multiply A times X. So we have that A times X. We have that A times X will equal to 3 minus 1. Okay, geometrically, what does this mean? If I have my sketch here, right? 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay, minus 1, minus 2, minus 3, minus 1, minus 2, minus 3, 1, 2, 3, 1, 2, 3. Now, this is vector X, 1, 0. So this is X here. This X, right? And we have that AX equals to 3 minus 1. 3 minus 1. So here. So this is AX. What do you realize? That originally this is the vector X. When we multiply it by matrix A, we got AX, which is not in the same direction as vector X. So this vector X will not be an eigenvalue of matrix A. Now, if we have a look on another vector y, 0, 1, right? And if we multiply it by A, what do we have? We have minus 1, 3, right? If you multiply matrix A times vector y, you have minus 1, 3. So if we represent y, which is 0, 1, this is y here, right? And then we see that ay is minus 1, 3, minus 1, 3. So this is somewhere here. So this is ay. So we can see that originally originally vector y is going upward here, as you can see y here. But after multiplying by a, it is now inclined to this direction. So we see that the vector y does not preserve the same direction. So even this vector y cannot be an eigenvector of matrix A, right? So I hope you're understanding how we are defining our eigenvector of a square matrix. Now, let's look at another example. Consider a vector z equals to 1 minus 1, right? If you multiply a times z, what will you have? Sorry, if you multiply a times z, what will you have? Multiplying a times z, what will you have? You have that, it will give you 4 minus 4, right? Which is equals to 4 times 1 minus 1. So, what can you see? We can see here that vector z multiplied by a keeps the vector az or the vector z in the same direction, just that it is multiplied by a scalar 4. That is, the equation az equals to 4z, which is the same as this equation. We can see that z, therefore, is a special eigenvector for matrix A for a special eigenvalue 4. Now, secondly, how do we compute eigenvalues and eigenvectors? Now, to compute or to find the eigenvalues of a vector, we solve the equation determinant of A minus lambda I equals to 0. And this will give you, and this will proceed to a polynomial equation or a characteristic equation of lambda, where lambda or the eigenvalues of matrix A will be the root solution of this polynomial. That is, P lambda equals to determinant of A minus lambda I equals to 0. Right? Now, how do we compute the eigenvector of A? Remember this equation. We have that AV equals to lambda V. Now, having known already the eigenvalues of the matrix A, we can easily solve for the eigenvector. This will give A V minus lambda V, which will be equals to A minus lambda I V, right? Which will be equal to 0. So to solve or to find the eigenvalues, the eigenvector, sorry, of this of A, we have to solve this equation. So we have that A minus lambda I V equals to 0. So this is, we call this equation 2, and we call this equation 1. So this will be the equation to solve in order to find the eigenvectors of A. Now, let's have in the next video, we will have more exercises with you, and we will let you know how practically we can find the eigenvalues of a square matrix and then complement its eigenvectors. Thank you very much. See you in the next video.